Hello student, in today's class we will study about developments leading to Bohr's model of atom. This is a part of the unit 2 part 2, that is structure of atom of class 11 chemistry. This is a very descriptive chapter where we are going to study about wave nature of electromagnetic radiation, particle nature of electromagnetic radiation, Planck's quantum theory, photoelectric effect, dual behavior of electromagnetic radiation, evidence for quantized electronic energy levels, that is atomic spectra, line spectrum of hydrogen. This is a very important and interesting chapter. Please note down all the important points. I welcome you once again. Developments leading to Bohr's model of atom. Historically, results observed from the studies of interactions of radiations with matter have provided immense information regarding the structure of atoms and molecules. Niels Bohr utilized these results to improve upon the model proposed by Rutherford. Two developments played a major role in formulation of Bohr's model of atom. These were dual character of electromagnetic radiation, which means that the radiations possess both wave-like and particle-like properties. Experimental result re- regarding atomic spectra. James Maxwell in 1870 was the first to give a comprehensive explanation about the interaction between charged bodies and behavior of electrical and magnetic field on macroscopic level. Wave nature of electromagnetic radiation. Maxwell in the year 1870 suggested that when electrically charged particles move under acceleration, alternating electrical and magnetic fields are produced and transmitted. These fields are transmitted in the form of waves called electromagnetic waves or electromagnetic radiation. Maxwell was once again the first to reveal that light waves are also associated with oscillating electric and magnetic character. Please see the diagram shown on the screen. The figure shows three axes, x-axis, y-axis and z-axis. There is a wave electric field component, red, which is moving in the z plane and it moves in the z plane as shown in the figure. Similarly, there is a magnetic field along the y plane which is shown in the blue color, and this is also moving in the direction of x. So both electric field component and magnetic field component are mutually perpendicular to one another and they move in the direction of propagation in the x-axis. The oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other and both are perpendicular to the direction of propagation of the wave. Unlike sound waves, the waves produced in water, electromagnetic waves do not require medium, hence they can move in vacuum also. It is now well established that there are many types of electromagnetic radiations which differ from one another in the wavelength and frequency. This will be shown in the electromagnetic spectrum. These constitute what is called electromagnetic spectrum. Wave nature of electromagnetic radiations, that is Maxwell's wave theory. Energy is emitted continuously from any source in the form of radiations traveling as waves and are associated with electric and magnetic fields perpendicular to each other and to the direction of propagation. These waves are called electromagnetic waves or electromagnetic radiations, as we have seen earlier. These components have same wavelength, same frequency, speed as well as amplitude, but they vibrate in two mutually perpendicular planes. Characteristics of electromagnetic waves. Frequency. Number of waves that pass a given point in 1 second is called the frequency. So, frequency is the number of waves that pass a given point in 1 second, and its SI unit is Hertz or cycles per second. It is named after the scientist Hertz. The next characteristic is defined by wavelength, and it is represented by the symbol Greek letter lambda. It is defined as the distance between any two consecutive crests, that is peaks or troughs. The SI unit of wavelength is meter, but it is expressed in Armstrong units, represented by the symbol capital A with a dot at on the head. Its value is 10 to the power of minus 10 meters. PM, that is 10 to the power of minus 12 meters, or nanometer, that is 10 to the power of minus 9 meters. The next parameter is velocity, represented by the letter C. It is the linear distance traveled by a wave in 1 second. Please note, it is the linear distance. In vacuum, all types of electromagnetic waves travel with the same speed, that is speed of light, 3 into 10 to the power of 8 meters per second. And the relationship between velocity and wavelength is C is equal to nu into lambda. Well, nu is the frequency. Wave number. Wave number is represented by nu bar. See, it is represented by nu bar. It is the number of wavelengths per unit length, or its unit is per meter or per centimeter. So, wave number nu bar is the number of wavelengths per unit length, and its unit is per meter or per centimeter. Amplitude. The height of crest or depth of a trough is called of a wave is called amplitude. It determines the intensity of brightness of the beam of light. Now, the relationship between frequency, wavelength and velocity can be written as C is equal to nu lambda, or nu is equal to, that is frequency nu is equal to C by lambda. Thus, a wave has a shorter length. A wave has shorter wavelength for higher frequency. That means the frequency is high, the wavelength is short. And if frequency is low, then wavelength is long. So, the relation between wave number and wavelength can be expressed as wavelength nu bar is equal to 1 over lambda. That is, wave number is the reciprocal of wavelength. Electromagnetic spectrum. Different regions of spectrum are identified by different names, like long radio waves, AM, FM, microwave, infrared, ultraviolet, X-rays and gamma rays, and their frequencies are shown on the screen in the diagram. So the frequency starts from almost right side 10 to the power of 0 says, and it extends up to 10 to the power of 24 Hertz and beyond. Some of the examples are radio frequency region around 10 to the power of 6 Hertz used for broadcasting. These are used up for broadcasting. Microwave region around 10 to the power of 10. Infrared region around 10 to the power of 13 Hertz used for heating. Ultraviolet region around 10 to the power of 16 Hertz is a component of sun's radiation. There is a small portion around 10 to the power of 15 Hertz is what is called the visible light. This is the region of visible light or visible spectrum whose wavelength varies from 400 to 700 nanometers. It is only this part which our eyes can see or detect. Special instruments are required to detect the non-visible radiation. All these are non-visible radiations. Different kinds of units are used to represent electromagnetic radiations. The radiations are characterized by the properties, namely frequency nu and wavelength lambda. This we have studied in the just gone through in the previous slide. Now let us quickly solve some numerical examples of electromagnetic waves. Example number 3. The Vivid Bharati station of All India Radio, Delhi broadcast a frequency of 1368 kHz. Calculate the wavelength of electromagnetic radiation emitted by the transmitter. Which part of the electromagnetic spectrum does it belong to? So we have to calculate the wavelength. Answer. We have to apply the formula which we knew, lambda is equal to c by nu, where lambda is the wavelength and c is the velocity of light and nu is the frequency. So we have to remember the velocity of light as 3.0 into 10 to the power of 8 meters per second. So substituting the values, 3.0 into 10 to the power of 8 meters per second, and nu is equal to, it is given as 1368 kilohertz. Simplifying, we get the result as 219.3 meters. This is the characteristics radio wavelength. Next question. The wavelength range of visible spectrum extends from violet 400 nanometers, that is 400 into 10 to the power of minus 9 meters, to red light, that is 750 nanometers, that is 750 into 10 to the power of minus 9 meters. Express these wavelengths in frequencies, that is Hertz frequency. Express these wavelengths in frequencies, Hertz. So 1 nanometer is equal to 10 to the power of minus 9 meters. Answer. Frequency of violet light is given by nu is equal to c by lambda. So c is the 3.00 into 10 to the power of 8 meters per second, and lambda is 400 nanometers. That is 400 into 10 to the power of minus 9 meters. And its value, by calculating and substituting the values, we get it as 7.5 into 10 to the power of 14 Hertz. Now we will do the same calculation for red light. So red light also, the formula is same. Nu is equal to c by lambda, that is 3.0 into 10 to the power of 8 meters per second divided by 750 into 10 to the power of minus 9 meters. This is the value given for red light. Hence, simplifying, we get the value as 4.0 into 10 to the power of 14 Hertz. Hence, the range of visible spectrum is from 4 into 10 to the power of 14 to 7.5 into 10 to the power of 14 Hertz in terms of frequency units. Next question. Calculate the wave number and frequency of yellow radiation having wavelength 5800 Armstrongs. Now first we will calculate the wave number. We know that wave number is 1 by lambda. First let us calculate the given values of lambda 500 in terms of meters. So lambda is equal to 5800 Armstrongs. That becomes 5800 into 10 to the power of minus 8 centimeters, and that converted to again meter, it becomes 5800 into 10 to the power of minus 10 meters. So therefore, wave number nu bar is equal to 1 over lambda, that is 1 over 5800 into 10 to the power of minus 10 meters. Simplifying, we get the value as 1.724 into 10 to the power of 6 per meter. Or we can write it also as 1.724 into 10 to the power of 4 per centimeter. Next we will calculate the frequency nu. Nu is given by the formula. Nu is equal to c by lambda. Velocity of light, c, the value of c is 3.00 into 10 to the power of 8 meters per second divided by 5800 into 10 to the power of minus 10 meters. That is the value we have calculated. It is given 5800 into 10 to the power of minus 8, that is equal to 5.172 into 10 to the power of 14 cycles per second, that is Hertz. Particle nature of electromagnetic radiation. Though the experimental phenomenon such as diffraction and interference was explained by the wave nature of the electromagnetic radiation, some of the following observations could not be explained with the help of electromagnetic theory of classical physics. Here, when we say diffraction and interference, diffraction is the bending of wave around an obstacle, and the interference is the combination of two waves of same or different frequencies to give a wave whose distribution at each point of space is the algebraic or vector sum of disturbances at that point, resulting from each interfering wave. So this theory, the classical physics theory, could not explain the nature of blackbody radiation, ejection of electrons, that is photoelectric effect, the variation of heat capacity of solids as a function of temperature, and the line spectra of atoms with special reference to hydrogen. These phenomena indicate that systems can take only one discrete amounts. All possible energies cannot be taken up or radiated. The first concrete explanation for this shortcoming, that is for the phenomena of blackbody radiation, was given by Max Planck in 1900. Max Planck, who lived between 1858 to 1947, was a German physicist who received his PhD in theoretical physics from University of Munich in 1879. In the year 1888, he was appointed director of Institute of Theoretical Physics at the University of Berlin. Planck was awarded Nobel Prize in Physics in the year 1918 for his quantum theory. Planck also made significant contributions in thermodynamics and the other areas of physics. So he explained the blackbody radiation. So what is blackbody radiation? An ideal body which emits and absorbs radiations of all frequencies uniformly. That means it absorbs all frequencies and radiates also all frequencies, and it is called a blackbody radiation. And the radiation emitted by such a body is called blackbody radiation. In practice, no such body exists. Carbon black is nearly approximates to the black body. A good physical approximation to a black body is a cavity with a tiny hole which has no other opening. A ray entering the hole will be reflected by the cavity walls and will be eventually absorbed by the walls. We will study about these things in subsequent slides. Planck's quantum theory. The amount of light emitted, that is intensity of radiation, from a black body and its spectral distribution depends only on its temperature. At a given temperature, the intensity of radiation emitted increases with the increase of wavelength and reaches its maximum value at a given wavelength and then starts decreasing with further increase of wavelength as shown in figure above. See, in this figure, you see here is plotted the wavelength and the intensity. If we keep the temperature constant and vary the wavelength, the intensity increases and then falls down. So at a different temperature, different graphs are observed. Also, as the temperature increases, maxima of curve shifts to shorter wavelengths. Shorter wavelengths, and several attempts were made to predict the intensity of radiation as a function of wavelength. But results of the above experiments could not be explained satisfactorily on the basis of the wave theory of light. Hence, a black body is also a perfect radiator of radiant energy. Furthermore, a black body is in thermal equilibrium with its surroundings. It radiates some amount of energy per unit area as it absorbs from the surrounding in any given time. Max Planck arrived at a satisfactory relationship by making an assumption that absorption and emission of radiation arises from oscillator, that is, atoms in the wall of black body. Their frequency of oscillation is changed by interaction with oscillators of electromagnetic radiation. Planck assumed that radiation could be subdivided into discrete chunks of energy. He suggested that atoms and molecules could emit or absorb energy only in discrete quantities and not in a continuous manner. Please repeat once again. Planck suggested that atoms and molecules could emit or absorb energy only in discrete quantities and not in a continuous manner. He gave the name quantum. So the name quantum was given to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. The energy E of a quantum of radiation is proportional to its frequency nu and is expressed by the equation E is equal to h nu. Let it be equation 6. The proportionality constant h here in the equation 6 above is known as Planck's constant and has a value of 6.626 into 10 to the power of minus 34 joules second. So here E is equal to 0 or h nu or 2h nu or 3h nu, that is integral multiple. N is the integral multiple. With this theory, Planck was able to explain the distribution of intensity in radiation from a black body as a function of frequency or wavelength at different temperatures. In the year 1887, Hertz performed a very interesting experiment in which electrons were ejected when certain metals like potassium, rubidium, cesium, etc. were exposed to a beam of light as shown in the figure. This figure shows equipment for studying the photoelectric effect. Light of a particular frequency strikes a clean metal surface inside a vacuum chamber. This is a vacuum chamber. This light strikes a metal surface made up of either potassium, rubidium, or cesium. Electrons are ejected from the metal or counted by a detector that measures their kinetic energy. So these electrons are emitted from this and it is directed towards the detector and it counts the number of electrons and measures their kinetic energy. It measures the kinetic energy. The results observed in the experiment were the number of electrons ejected from the metal surface as soon as the beam of light strikes the surface. There is no time lag between the striking light of beam and the ejection of electrons from the metal surface. There is no time lag. Second point is the number of electrons ejected is proportional to the intensity or brightness of the light. So number of electrons ejected is proportional to the brightness or intensity of the light. For each metal, there is a minimum frequency called characteristic frequency or threshold frequency below which the photoelectric effect is not observed. At the frequency nu greater than nu naught, the ejected electrons come out with certain kinetic energy. The kinetic energy of these electrons increase with increase of frequency of the light used. That means if you increase the frequency of this incident light, the kinetic energy also increases. All the above results could not be explained on the basis of classical physics. According to classical physics, the energy content of the beam light depends on the brightness of light, whereas it was not so. Thus, the number of electrons ejected and kinetic energy associated with them should depend on the brightness of light. It has been observed that though the number of electrons ejected does not depend on the brightness of light, the kinetic energy of ejected electron does not. So the kinetic energy does not depend on the brightness. For example, red light with a nu equal to 4.3 to 4.6 into 10 to the power of 14 Hertz of any brightness or intensity may shine on a piece of potassium metal for hours, but no photoelectrons are ejected. But as soon as even a weak yellow light, see when red light falls, no electrons are ejected, but when a weak yellow light falls, which is of the range 5.1 to 5.2 10 to the power 14 Hertz, shines on potassium metal, the photoelectric effect is observed. Thus, the photo threshold frequency nu naught for potassium is 5.0 into 10 to the power of 14 Hertz. Einstein's photoelectric effect. In the year 1905, Einstein explained the photoelectric effect using Planck's quantum theory of electromagnetic radiation as a starting point. Albert Einstein was a German-born American physicist who is regarded as one of the greatest physicists of the world. His research paper on special relativity, Brownian motion, and photoelectric effect have influenced the development of physics. He received the Nobel Prize in Physics in the year 1921 for his explanation of photoelectric effect. According to him, when a photon of sufficient energy strikes an electron in the atom of a metal, it transfers its energy instantaneously to the electron during the collision and the electron is ejected without any time lag or delay. The greater the energy possessed by the photon, greater will be the transfer of energy to the electron, and greater the kinetic energy of the ejected electron. In other words, the kinetic energy of the electron is proportional to the frequency of the electromagnetic radiation. Since the striking photon has energy equal to h nu and the minimum energy required is h nu naught, which is called h nu naught is also called work function w naught, then the difference in energy h nu, that is incident energy minus threshold energy, that is the minimum energy, is transferred as the kinetic energy of the photoelectron. This is represented by the equation h nu is equal to h nu naught plus half me square. Here in this equation 7, me is the mass of electron and nu is the velocity associated with the ejected electron, that is the term nu on the left hand side. The more intense is the beam of light, the larger is the number of photons. Consequently, the number of electrons ejected is also larger. The work function of few metals used in photoelectric devices are shown in the figure on the screen. The work function is W naught per electron volt. So for metal lithium, work function is 2.42, Na 2.3, potassium 2.25, magnesium 3.7, copper 4.8, and silver it is 4.3. Dual behavior of electromagnetic radiation. Light behaves either as a wave or as a stream of particles. When radiation interacts with the matter, it displays particle-like properties. On the other hand, when it propagates, it displays wave-like properties. Though it could explain the black body radiation and photoelectric effect satisfactorily, but it was not consistent with the known wave behavior of light, which could account for the phenomena of interference and diffraction. This dilemma was solved by accepting the idea that light possesses both particle and wave-like properties. That is, light has a dual behavior. Depending on the experiment, we find that the light behaves either as a wave or as a stream of particles. Whenever radiations interact with the matter, it displays particle-like properties in contrast to wave-like properties. That is interference and diffraction, which it exhibits when it propagates. Let us solve some numerical examples. First one, calculate energy of 1 mole of photons of radiation whose frequency is 5 into 10 to the power of 14 Hertz. Answer, energy E is given by the relation E is equal to h into nu, where h is Planck's constant and nu is the frequency. So given value we have to remember is Planck's constant h is 6.626 into 10 to the power of minus 34 joule seconds, and light photons frequency is nu equals 5 into 10 to the power of 14 per second. Therefore, substituting in the given equation, E is equal to h nu, these values we get the answer as 3.313 into 10 to the power of minus 19 joules. So, energy of 1 mole of photons is equal to 3.313 into 10 to the power of minus 19, that is the energy, into 6.022 into 10 to the power of 23 per mole. Therefore, the answer is 199.51 kilojoules per mole. Next example, a 100-watt bulb emits monochromatic light of wavelength 400 nanometer. Calculate the number of photons emitted per second by the bulb. Power of the bulb is given as 100 watts, that is equal to 100 joules per second. That is 1 watt is equal to 1 joules per second. Therefore, energy of photon is given by relation E is equal to h nu, and the nu, that is the frequency, is c by lambda. Substituting the values, we get energy of one photon is equal to 4.969 into 10 to the power of minus 19 joules. So therefore, the energy of photons emitted is equal to 100 joule per second divided by the energy of one photon. So we get the energy as 2 into 10 to the power of 20 per second. Question number 8. The threshold frequency nu naught for a metal is 7.0 into 10 to the power of 14 per second. Calculate the kinetic energy of an electron emitted when radiation of frequency nu is equal to 1 into 10 to the power of 15 per second hits the metal. Let us solve it. Applying Einstein's equation of kinetic energy, we get, that is given by half me into v square is equal to h of nu minus nu naught. Here me is the mass of electron, nu is the frequency of the emitted electron, and nu naught is the threshold frequency. H is the Planck's constant. Substituting the values, we get the answer as 1.98 into 10 to the power of minus 19 joules. Evidence for the quantized electronic energy levels, that is atomic spectra. The speed of light depends upon the nature of the medium through which it passes. As a result, the beam of light is deviated or refracted from its original path as it passes from one medium to another. It is observed that when a ray of white light is passed through a prism, the wave with the shorter wavelength bends more than the one with a longer wavelength. Since ordinary white light consists of waves with all wavelengths in the visible range, a ray of white light is spread into a series of color bands called spectrum. The light of red color, which has longest wavelength, is deviated the least, while the violet light, which has the shortest wavelength, is deviated the most. The spectrum of light, the spectrum of white light, which ranges from violet at 7.5 into 10 to the power of 14 Hertz to red at 4 into 10 to the power of 14 Hertz, is an example of a continuous spectrum. Continuous because the violet merges into blue, blue into green, and so on. A similar spectrum is produced when a red bow forms in the sky. Let us recall that the visible light is just a very small portion of electromagnetic radiation or electromagnetic spectrum. Emission spectrum. The spectrum of radiation emitted by a substance that has absorbed energy due to heating or otherwise is called an emission spectrum. Atoms, molecules, or ions that have absorbed radiations are said to be excited. To produce an emission spectrum, energy is supplied by heating or irradiating it, and the wavelength of the radiation is emitted. Absorption spectrum. An absorption spectrum is like a photographic negative of an emission spectrum. A continuum of radiation is passed through a sample which absorbs radiation of certain wavelength. The missing wavelength, which corresponds to the radiation absorbed by the matter, leaves dark spaces in the bright continuous spectrum. Please see the figure here on the screen. The figure shows the top one, you can call it as A, is an atomic emission. The light emitted by a sample of excited hydrogen atom. Here there is an hydrogen atom which is excited. Or you, as a matter of fact, you can take some other element also. Can be passed through a prism. That is, light is passed through a prism and separated into certain discrete wavelengths. Thus, an emission spectrum, which is a photographic recording of separated wavelengths, is called spectrum. Any sample of reasonable size contains enormous number of atoms. Although a single atom can be in only one excited state at a time, the collection of atoms contain all possible excited states. The light emitted as these electrons or as these atoms fall to a lower energy state is responsible for the spectrum. The figure B shows the atomic absorption spectrum. So this is atomic absorption spectrum. When the white light is passed through the unexcited atomic hydrogen, then through a slit and prism, the transmitted light is lacking in intensity and the same wavelengths are emitted as in A. The recorded absorption spectrum is also a line spectrum and the photographic negative of the emission spectrum. Here it is unexcited atom and this is an excited atom, and here you can see the increasing wavelength. As an increasing wavelength it becomes dark spots, whereas this is an absorption spectrum. It is exact negative of the emission spectrum. Spectroscopy and line emission spectra. The study of emission or absorption spectra is referred to as spectroscopy. The spectrum of visible light was continuous as all wavelengths, that is red light to violet light, of the visible light are represented in the spectra. Line emission spectra. The emission spectra of atoms in the gas phase, on the other hand, do not show a continuous spread of wavelength from red to violet. Rather, they emit only at specific wavelengths with dark spaces in between them. Such spectra are called line spectra or atomic spectra because the emitted radiation is identified by the appearance of bright lines in the spectra. Line emission spectra are of great interest in the study of electronic structure. Each element has a unique line emission spectrum. The characteristic lines in an atomic spectra can be used in chemical analysis to identify unknown atoms in the same way as fingerprints are used to identify people. The exact matching of lines of emissions spectrum of atoms of a known element with the lines from an unknown sample quickly establishes the identity of the latter. German chemist Robert Bunsen, who lived between 1811 to 1899, was one of the first investigators to use line spectra to identify elements. Elements like rubidium, caesium, thallium, indium, gallium, and scandium were discovered when their minerals were analyzed by the spectroscopic methods. The element helium was discovered in the Sun by spectroscopic method. Line spectrum of hydrogen. When an electric discharge is passed through gaseous hydrogen, the H2 molecules dissociate and energetically excited hydrogen atoms emit electromagnetic radiation of discrete frequencies. The hydrogen spectrum consists of several series of lines named after their discoverers. Balmer showed that if spectral lines are expressed in terms of wave number, then the visible lines of hydrogen spectrum obey the following formula, and the formula is wave number nu bar is equal to 109 comma 677 into 1 over 2 square minus 1 over n square per centimeter. Let it be equation 8. The value of 109,677 per centimeter is called Rydberg constant for hydrogen, where n is an integer. Here in this equation 8, n is an integer whose value is greater than or equal to 3. That is, n is equal to 3, 4, 5, etc. These series of lines are called Balmer series. Balmer series of lines are only lines in hydrogen spectrum which appear in the visible range of the electromagnetic spectrum. All other lines are not visible. In the figure shown, the transition of electrons from the figure shows transitions of electrons in the hydrogen atom. The diagram shows the Lyman, this is the Lyman series, Balmer series and Bastian series, only three. And out of these three, only this Balmer series is visible. The Swedish spectroscopist Johannes Rydberg noted that all series of lines in the hydrogen spectrum could be described by the expression nu bar is equal to 109,677 into 1 over n1 square minus 1 over n2 square per centimeter. Let it be equation 9. Here n1 is equal to 1, 2, etc., 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 and n2 is equal to n1 plus 2. The first 5 series of lines that correspond to N1 equals 1, 2, 3, 4, 5 are known as Lyman, Palmer, Paschen, Brackett and Pfund series. Out of this, Lyman, Balmer and Paschen are shown in the diagram. The hydrogen atom has the simplest line spectrum. Line spectrum becomes more and more complex for heavier atoms. The features which are common to all the line spectra are line spectrum of element is unique. So it is unique for each element line spectrum, and there is regularity in the line spectrum of each element. Table appearing on the screen also shows the values of N1 and N2 given in equation number 9 for different series like Lyman, Balmer, Paschen, Brackett and Pfund. The values of N1 are 1, 2, 3, 4, 5 respectively, and N2 is corresponding N values of N2 are 2, 3, 3, 4, 4, 5, 5, 6 and 6, 7. The region, spectral region is ultraviolet region, Balmer is visible region, and Paschen, Brackett and Pfund all fall under infrared region. Next we will take up some objective type of questions. Next we will take up some multiple choice questions. Question number 1. Choose the component, the correct statement related to electromagnetic waves shown in the figure. A, B and C, 4 options are given and you have to read. Please read all of them and answer the question. So you have to remember that electromagnetic waves have these components have same wavelength and both vibrate in perpendicular planes. Waves can travel in vacuum and all the 3 are common and correct. What will be the wave number of the yellow radiation having lambda is equal to 240 nanometers? 4 options are given. You have to analyze and calculate the value. The calculation is shown on the screen in the insert box, and wave number can be calculated by using the formula nu bar is equal to 1 over lambda. And by substituting you will get the value as 4.16 into 10 to the power of 6 per meter. So this answer appears in as part B. Please mark it. Next question is, what will be the energy of 1 photon of radiation whose frequency is 5 into 10 to the power of 14 per second? 4 answers are given. You have to analyze. So analyze, the calculation is shown in the insert box. E is equal to h nu. H is a Planck's constant, you have to remember, and the frequency is given as 5 into 10 to the power of 14 per second. So the value comes to 3.3 into 10 to the power of minus 19 joules. This answer appears as option B. Please mark it. Next question, what will be the energy of a photon which corresponds to a wavelength of 0.5 Armstrong? So 4 options are given and you have to make calculations. Using the formula E is equal to h nu, that is once again equal to h into c by lambda. So you substitute the values and the answer comes to 3.98 into 10 to the power of minus 15. So this answer comes as option A. Please mark it. Next question. Compare the energies of two radiations, E1 with wavelength 800 nanometer and E2 with wavelength 400 nanometers. And you have to identify the relationship between E1 and E2. Four options are given. You please read it and let us make calculation. E1 is equal to, we have to use the same formula. E1 is equal to h into c by lambda 1. E2 is equal to h into c by lambda 2. Therefore, E1 by E2 is equal to lambda 2 by lambda 1. So, the ratio is 1:2. Therefore, E2 will be equal to 2 times E1. So, option C is the correct answer. Next question. Electromagnetic radiations of lambda is equal to 242 nanometer is just sufficient to ionize the sodium atom. What is the ionization energy of sodium per atom? Once again, this is a numerical problem. You have to apply the formula and substitute the values. Calculations are shown in the figure where lambda value is given, and we have to remember the value of Planck's constant and calculate. The answer comes to 8.214 into 10 to the power of 9 minus 19 joules per atom. This answer is available as option B. Option C. Please mark it. Question number 7. The energy difference between the ground state of an atom and its excited state is 3.3 into 10 to the power of minus 19. So this is the energy difference, that is delta E. What is the wavelength of photon required for this transition? Four values are given in the table. You read all the four values and you have to calculate the energy difference. Delta E is equal to hc by lambda. Therefore, lambda is equal to h 6.6 into 10 to the power of minus 34 joules, and velocity of light is known, and lambda is 3.3 into 10 to the power of minus 19. Hence, the answer is 6.6 into 10 to the power of minus 7 meters. This answer is given as option D. Please mark it. Next question. Question number 8. This question is already answered in the numerical problem. Please go back and follow it and do the calculations as shown on the screen and mark the correct answer. And the correct answer is 2 into 10 to the power of 20 per second. This we come to the conclusion of part 2.3. And next we will take up Bohr's model for hydrogen atom. Till then, goodbye.